So we were talking about a shrinking core model. A couple other things for you to think about. As I mentioned, it could be either kinetically controlled or diffusion controlled. And again, one thing you may want to start thinking about is what are typical Lewis numbers in a condensed phase? What's easier to transport, heat or mass in a condensed phase? So likely the heat's going to be transported quicker than the oxidizer or the fuel element. So then you can start seeing, well, potentially, even though the particle's very small, I could have diffusion-controlled processes across that oxide layer. And if that's the case, if you take a look at this bottom right plot, another thing to think about, what is plotted here is essentially the conversion versus the conversion rate. Okay, and the line here is for a diffusion-controlled process. And as you would expect, what happens is during the first 10 or 20% of conversion of, say, the metal, I'm going to have a very fast conversion rate. And then once 20% of the metal has been consumed, because that oxide layer's gotten so thick, the conversion rate's going to slow down significantly. So again, thinking about a nanoparticle, I mentioned, a good bit of the atoms are near the surface. So if this particle's reacting and it doesn't store much energy to raise its overall temperature, do I need to really consume a significant layer of the atoms deep into the surface to get a very hot temperature that would propagate a reaction? Right? And it may be true that all I need to do is consume an atom layer or two, and I got enough heat release because these reactions are going to be very exothermic to raise the nanoparticle temperature, and that would be enough basically to propagate a reaction in a system if I wanted to. Now there's been many theories that have been proposed how nanoparticles can react and even micron particles. I showed you those ignition temperature data plot as a function of diameter. And the general idea is if I'm heating up say an aluminum particle, the expansion during melting of the aluminum basically puts stress on the oxide layer, which hasn't melted. So I can build up an internal pressure as the particle's heating up. And that internal pressure can crack the oxide layer. And if it cracks the oxide layer, then I can have molten aluminum diffuse through that crack towards the oxidizer, and it can react with oxygen to release heat. And that process could continue to slowly raise the temperature up to the ignition temperature. One of the other mechanisms that's been proposed, particularly for small particles, is suppose I introduce a large heating rate onto the particle, such that now as the particle heats up, which it's going to do very quickly, and if it heats up uniformly and I got a uniform thickness oxide layer around it, during that expansion process, I essentially disrupt that oxide layer all at once. And that's been referred to as the melt dispersion mechanism for high heating rates. Okay, so as that happens then, basically I have an aluminum core covered with an initial aluminum shell. The fast melting of the aluminum leads to spallation of the aluminum shell, and as a consequence, the unloading wave propagates to the center of the molten aluminum core and generates tensile pressure, which disperses, in this case, small aluminum clusters instead of just gaseous aluminum, which has been said to really enhance then the oxidation rate because I'm really throwing out these small particles. Now, there's also been some interesting molecular dynamics calculations done. And this is particularly valuable, if I'm dealing with very small particles because I can do that computationally then. And in these calculations, there's been different codes developed to basically, instead of just doing an MD calculation, to put in a reactive force field so that I can account for some of the chemistry. And what these calculations have shown is that if I look at a nanoparticle, as shown in the upper left here, again, I have my aluminum and then an oxide layer around it. As the particle heats up, what initiates the reaction? In this particular case here, what the molecular dynamics calculations say is it's the aluminum that starts reacting with the aluminum oxide. So I've got some sort of reaction that says Al's reacting with Al2,3 at that interface. And what it does is it ends up reducing this to an AlXOY, okay? And that reduction is a little bit exothermic that raises the temperature, okay? And then that continues to the point where everything becomes molten, and then I start getting diffusion of aluminum and oxygen across the layer itself. So as I note here on the left, as oxidation begins, due to expansion of the molten core, the size grows. Oxidation dynamics start with the aluminum nanoparticle at the core shell interface. When the molten aluminum reacts with the alumina shell, taking oxygen, form aluminum-rich AlXOY clusters, which generates heats. The shell does not break or shatter, it only deforms, and when the temperature gets up to basically the vaporization temperature, the aluminum shell melts, and the aluminum ejections occur at the aluminum nanoparticle into oxygen environment, producing oxygen-rich aluminum oxide clusters. So again, you can see the, different types of analysis are leading us to different types of interpretation of really the combustion process. This is another result that is interesting. These are slow heating rate experiments in a thermogravimetric analyzer. So again, I put some nanoparticles in a cup and I slowly heat them and I look at what the mass loss is or what the exothermicity is at a particular temperature. And so in this particular case, the nanoaluminum was reacting with CO2. And if I follow the curves here, and I look at different size particles, for example, 38 nanometers all the way up to 10 micron. Note that the melting temperature of the aluminum is right here. So you can see the energy went negative, requiring energy. So this is the melting temperature. For the very small particles, at about 500 or so, I'm getting heat release. So that says there's actually a solid state reaction. Right? Neither of the components have melted, and I'm getting diffusion in the solid state for reaction to occur. And if you notice then, when that occurs, then the mass is gained on the particles. So in other words, the CO2 is yielding oxygen, which is forming aluminum oxide, and the sample mass is increasing. And for the micron particles, you can see melting occurs, and then it's not until a higher temperature where the mass gain starts to occur. So the one thing I wanted to show you there is that, in these small particles with small length scales, one can actually have solid state reactions in addition to liquid phase reactions and gas phase reactions. There's been different theories how ignition occurs, as I just said. One of the theories also says that the phase transformations of the oxide layer becomes very important as the particles heat up. Okay, so if I go from amorphous to gamma aluminum oxide transition, the densities of those two oxides change, and as a consequence of that, I can open up regions on the surface where, again, oxygen can diffuse through the pores and start to react with the surface to raise the temperature a little bit to continue the ignition rate. And then the same thing can happen as I go from gamma to delta and alpha aluminum. And so the phase transformations of the oxide itself can become very important in the ignition process. And this was some nice experiments done by Mike Zachariah, in which he had a flow reactor. He created a sort of a stream of nanoparticles. He let them react, and he looked at basically the products being formed in a mass spectrometer. And what he finds here is if I'm looking at sort of the log of a reaction rate, for the larger particles, he finds effectively a larger activation energy, and for smaller particles, he finds a smaller activation energy necessary for reaction. Okay. Okay, so I want to say a few words about nanoparticle synthesis. How are they made? This is an example of showing, what's kind of been done early on. These are SEMs of nanoaluminum. As I mentioned, one of the early considerations is how do I prevent or how can I reduce the oxide layer and passivate the particle with something else? So here in this example on the right, the particle is made by wet chemistry, and during the particle formation, it was coated with a fluoropolymer instead of an oxide layer, which passivated it. These are particles. You can also have, in addition to nano metal particles, people have made nano oxidizer particles, for example, nano RDX. And on the right here, then, is, again, a different combination of taking nano iron particles, passivating it with aloic acid and other materials, and the idea of also taking Cl20 and coating it with nitrocellulose. And I'll give you a little bit more details, but what that's sort of indicating what I'm showing here. So imagine now, when we were talking about a composite propellant, remember I had a matrix, and in the composite propellant, I had my oxidizer particles, and I had my binder. And these length scales were all at the tens, if not hundreds, of micron. Okay, suppose I say I can now make a composite energetic material right at the nanoscale. Okay, so take a look at this sort of cartoon here. In the center here would be my nanoaluminum or smaller particle. And then what I do is I passivate it with ligands that have basically a CH structure, as shown here. And then I functionalize the tail end or somewhere on these ligands with an oxidizer, maybe NO2. So all within this nanoparticle now, I have my fuel, I have my binder, I have my oxidizer. Okay, and in fact, that's what that fluorocarbon particle essentially looked like that I showed you here. In the case of this, I have my nanoaluminum, and surrounding it, I have a fluoropolymer where the fluorine is acting as the oxidizer to make aluminum fluoride. Okay, so how are the nanoparticles made in general? The creation of nanoenergetics is still an area of current research. There's many approaches, exploding wires, condensation techniques, plasma methods, and wet chemistry approaches, and each have their advantage and disadvantage, particularly for scale up and safety. So I kind of just, I'm not going to go through all the references, but I'm giving you references if you're interested. You can sort of break the synthesis methods down into different groups, and what I list here is group 1 is gas phase condensation-based techniques for production of nanometal particles. So this is where I would electrically explode a wire. It would create vapor, and that vapor would condense, and I would control the condensation process. Okay, so also physical vapor deposition and vacuum, chemical vapor deposition, and supercritical processing. So in the case of supercritical processing, I might use it for the RDX particles that I just showed you. I'll show you an example where I dissolve essentially the RDX in supercritical CO2. I expand it, and during that expansion process, the RDX particles want to start to basically nucleate and form small particles, and I need to then control the growth of those particles. Group 2 I refer to as flame synthesis, which is maybe you've seen in combustion papers, where I use basically basically the heat from a flame and the materials I put in the flame to create the particles, or again using heat of a plasma or an arc. As group 3 is referred to as wet chemistry or sol gel chemistry. And in wet chemistry, then the particle actually forms in solution, And one of the advantages there is if I can coat it also in that solution, then the pure particles never exposed to air or oxidizer. And I can, group 4 here is mechanical alloy or activation. So all I do there is I take a large particle and I sort of start to grind it in a ball milling system where the continued grinding starts tearing off and making small particles. And often you'll do that in solution so that you can control the passivation as these small particles are formed. And group 5 is one that's still growing and being looked at using basically lithographic pattern techniques of various form then. And eventually, incorporating that sort of process into a 3D printing system. Okay, so I give one example here in which that nanoEnergetics was produced using high-pressure supercritical fluids. The idea was I would dissolve the RDX into supercritical CO2, and then as I expand it through a nozzle, nucleation sites are formed, the RDX starts to grow, and what you want to do then is you want to prevent the continued growth, so what you might have is a solution very near that where the particles then are gone into solution, and the solution then prevents their further growth. And you can see here, this is some SEMs of the particles themselves, the size distribution, etc. Okay. Okay, so the next thing I want, giving you a brief overview of metal combustion, large particles, small particles. What happens when we start adding these particles into an energetic material, like a AP, HTPB composite material? So as I mentioned here, aluminum is used as an ingredient in solid propellants because of its high energy density, high heat release during oxidation, low cost, and relative safety. Because most of the unaluminized propellants are already fuel-rich, it might seem counterproductive to add more fuel. However, the oxidation reduces the oxidizer vapors, water and CO2, the hydrogen and CO, which are better propulsive fluids because of their lower molecular weight. This, in combination with a large increase in temperature, results in an increase in the specific impulse of about 10% and a net gain in propellant mass fraction in the motor of approximately 15%. Aluminum, and even the modest amount, suppresses combustion instability problems common in motor development programs. However, there's also problems with the use of aluminum, such as the smoky exhaust, two-phase flow losses, and slag accumulation, for example, if it was used in a motor. Aluminum does not turn into vapor at the propellant surface like other primary ingredients. So I give you here some conditions. The boiling point of aluminum is about 2,500 degrees C. Usually the propellant surface temperature is 600 degrees C, which is about 60 degrees below the 660 degrees C melting point of aluminum. The density of aluminum is like 2.7 grams per cubic centimeter, which is about 1.38 times that of AP and 3 times that of the hydrocarbon binders. Its reaction or ignition on the surface is inhibited by the refractory oxide coatings on the particle surfaces. The melting point of aluminum oxide is like 2,100 degrees C, and aluminum oxide constitutes about 0.5% of the particle mass for 25 micron particles. So you can see, obviously, if I'm in the micron size, then the oxide mass is very small. These particles tend to adhere to the surface and binder melts, leading to locally higher concentrations. At temperatures between the aluminum and aluminum oxide melting points, leaking of aluminum from the oxide coating can lead to sintering and the assemblages of particles into sintered accumulates. The leakage can also be so great that the aluminum engulfs the entire assemblage to form spherical agglomerates. So I think I have some cartoons in a second. When aluminum particles are heated, the oxide structure changes and the aluminum expands. The coefficient of expansion of the oxide skin is less, so that it must be stressed. At the melting point of aluminum, it expands in volume about 6%, thereby stressing the oxide skin further and potentially causing cracks. The concentrations of a typically 20 micron particles can lead to coalescence into large droplets, typically 200 micron containing 10 to the third original particles. So the point is, even though I put, I'm designing a system with 20 micron diameter aluminum, by the time it comes off the surface, it could be quite a bit different in size. Large droplets leave the surface and burn in the gas flow field, typically with the water and CO2, whereas any original particles that leave the surface individually burn up within 1 to 2 millimeters of the surface, with a corresponding greater effect on the propellant burning. So how's the particles affecting it? Well, obviously, the radiative heat transfer back, because the flame temperature, remember, of aluminum is very high. It could be close to 3,800 Kelvin, which is much higher than the gas is going to be. In small motors, large droplets may not burn up completely, reducing the specific impulse. So I think I showed this figure before, so I'll just go through it real quickly. This is a typical composite propellant mixture having 88% solids loading, 12% binder, indicating the different coarse sizes or fine size and medium size ranges of the oxidizer, and the typical initial size of the aluminum. This is a picture of the large oxide particles and what it might look like in an AP composite propellant. So points, very heterogeneous burning surface. The dimensions don't allow for direct combustion measurements, and the crystals are not round. Typically, they have irregular shapes. And so this is what I might see then in the burning of a composite propellant. On the left is basically the old shuttle propellant burning. And a picture here was taken at an instant in time. And so this right here is where the surface was at this instant. And what you're seeing then is obviously the particles here are radiating, but below the surface you don't see the aluminum particle because obviously the temperature is low and it's in a condensed phase. But as they come to the surface, these particles can start growing because of the sintering process. They're melting and they're coming together. Okay, and so their size when they leave the surface can be much larger. And what you're seeing above it then, because of the convective gases from the binder decomposing and the AP basically having a monopropellant flame, that convective process drags the particles off the surface. And so these particles up here are burning in the gas phase above the surface. And if I were to look at this particle in natural luminosity and looking at its emission, what I would see is something like this. So this is where the agglomerate grew to about 200 micrometers in diameter. And what you can see then is, in this case here, this was a low pressure experiment. You can still see, this is the flame zone out here where the aluminum oxide particles are being formed, the nanoaluminum oxide, where the reaction's occurring. And you can see the convective flow about it that's dragging the particle off the surface, creating this tail. And then the tail back here, you can't see it very well, but there's a little dissimilarity here. There's essentially an oxide cap that's floating on the surface. And you can get recirculation of these particles out here, adding more aluminum oxide to the surface. So here's a video of that process. So you can see the aluminum coming out of the surface. It resides near the surface for a while, and then it leaves the surface. The other thing you notice, if I play it again, you'll see carbon layers also coming off of the surface. So some of the binder is not being completely oxidized. There was a chunk that just went off. So one of the, this is still at relatively low pressure. Eventually, if I get to higher pressure, it's still kind of hard to say in this video here, is this a detached flame off of the alumina agglomerate, or is it the flame structure getting very close? So what I did is I went back and I did some equilibrium calculations because I wanted to estimate the aluminum diffusion flame temperature as a function of pressure. And the way I did this was I first took a mixture of AP and HTPB in the right ratio that I just showed you before, and I calculated what was the adiabatic flame temperature. Then I assumed I had aluminum being injected into that equilibrium mixture, okay, with which its initial temperature was at the melt temperature of aluminum. So you can imagine, according to that picture I just had, here was my big chunk of aluminum. This got pretty close to the melt temperature of aluminum. Then it gets injected off. And this temperature up here, I assume, was the flame temperature already of the AP HTPB mixture. So essentially, the aluminum's burning in this temperature here in a mixture of H2O, the products of this, H2O, CO2, et cetera. Okay? And when I did that, then I brought the mixture together and I changed the ratio of that so I could find a maximum temperature. And what you found then is here's the boiling point temperature of aluminum, and here's the temperature I calculated, which was the maximum temperature of this molten aluminum burning in the products of APHCBB, followed this curve here. And so again, you can see I get this crossover temperature at about 7 atmospheres. So if I'm burning the aluminum in the products of a binder AP system at low pressure, I'm going to have detached flames likely. But if I get much higher, I'm going to see the surface reaction that potentially could occur. Okay, so here's some pictures of looking at this sintering and agglomeration process. So if I look at the top left, what the initial experiments were was just to take some aluminum particles and drop them on a hot plate and to photograph them over time and see what happens. So if you look at the top left, you'll see oxide skins on particles dropped on 1400 degrees C plate showing crack pattern and bridging between the particles. So you can see here some cracks forming here where molten aluminum could come out, and all of a sudden you're seeing the bridging between the particles. So effectively, these accumulates being formed, sintering process, and the particles would be getting bigger. Okay? And the picture there on the right basically shows a sintered, what's referred to as an accumulate, quenched in transition to an agglomerate. Note the spherical structures where coalescence of the liquid aluminum has started. And then as I go to the right, you can see this has grown further, where now you're seeing smaller particles being embedded in this gulf of molten aluminum. So the agglomerate quenched before complete transition to the molten droplet. The aluminum surface tension had drawn the accumulate into a sphere, but not yet closed the surface. Unmelted oxide shells still visible in the openings. So one of the questions, and this hasn't been answered, is the burning of one of these agglomerates that potentially have smaller particles inside them with oxide shells, do they burn the same way as a pure, aluminum particle that people study in very fundamental experiments? And that question really hasn't been looked at. Okay, so how do these agglomerates form? Again, through particle packing. The stoichiometry of an AP binder system dictates that a maximum achievable content of AP be used with required propellant processing and mechanical processes. So I need to put as much AP in the propellant as I can because that's where my oxidizer is coming from, right? But then I'm limited by the solid loadings because of the processing. If I put too much solids in, I got too much surface area, the viscosity changes very large and I can't work with it. Plus the mechanical characteristics, behavior will be poor at the very end of the of the mixing. So typically a coarse 200 micron AP portion is combined with the finer particles to fill the spaces left in the coarse particle array. By careful blending of the sizes, for example, using a trimodal particle size, formulations are processed with 86 to 88% AP by weight loadings, which is still fuel rich, that yield cured propellants with acceptable mechanical properties. When the aluminum is added, typically 10 to 30 micron, a corresponding volume of the fine AP is removed, okay? So I'm actually removing oxidizer particles as I add more fuel. Thus, the aluminum particles are pre-concentrated in pockets of the coarse AP packing pattern. And so here's an example of what you cartoon that you could envision that movie, what was happening in that movie that I showed you. Here's my coarse AP, the binder here, and what's down in here is also finer AP in my aluminum particles. Okay, so now this surface is going to be regressing down. And remember, the surface temperature is not necessary at the melting temperature or the ignition temperature of the aluminum. And so as the binder and AP burn, these aluminum particles start to accumulate in the pockets of the large AP particles. And they sit there for a while. And as they sit there for a while, their temperatures go up because they start extending further and further out into the flame zone. And then they can start melting, and you can start basically engulfing other particles. And finally, the particle will get hot enough, it might ignite, and then it basically gets carried away by the convective gases. So I note here then the size distribution of agglomerates on the surface depends on the structural features of the aluminum particle packing, the surface retention characteristics of the binder, for example, particle adhesion in a binder melt layer, retention in a carbonaceous surface structure, direct adhesion to the underlying aluminum particles, centrifugal forces and spinning motors, the susceptibility of individual particles to ignition, possible connective processes between the concentrating particles that lead to group behavior, and the evolution of the underlying structure in the hot overlying gas flamelets that lead to detachment and ignition events. So again, it's a very complicated process, and it's not been modeled very well and detailed. There are, overall global models, and that global model is typically referred to as the pocket model. This plot here shows the effective pressure on the mass average agglomerate size for bimodal propellants. So if I look at this plot as a function of pressure versus the diameter of the particles coming off for different AP particles, going from in terms of the medium size. So the coarse particle is always 390, and what's being adjusted here is the medium or finer AP in the composite. And so two things you observe right away. If I increase the pressure, the size of the agglomerates coming off the surface decrease. Okay, so the burning rate's increasing. And so the particles have less time to basically stay on the surface because the gas is pushing them off. The other thing you notice is as I change to smaller particles in between the larger particles, what that means is I'm essentially getting a larger volume for the aluminum to gather. Okay, so they can grow into larger agglomerates, they can sinter easier. Whereas if I have just large and large particles, then the aluminum is better separated from each other, more difficult to sinter it. Okay, so one of the questions is, I showed you in those simple ideal experiments, here's my aluminum and here's my aluminum oxide being formed in this detached flame. And I've already noted as I go to higher pressures, I'm going to expect this flame to come closer to the surface and essentially be on the original particle. One of the important questions is, what is the size of the aluminum oxide particles that's formed after reaction's complete? Do I have micron-sized particles? Do I have nanometer-sized particles? And that size distribution is very important particularly in rocket motors, because it creates two-phase flow losses, right? If I have a large particle that's going down through the nozzle, I've got to accelerate that particle, and that takes energy. The other advantage, though, is if I know that size distribution and I could anticipate some sort of instability in the motor, which is going to create pressure fluctuations, I could maybe tune the size of those particles so that as that pressure fluctuation changes a velocity fluctuation, those particles dampen out that particular frequency, depending on their size. Okay, so what this basically shows here is a typical size distribution of oxide particles. And what you'll note is there's a size range that's in 2 micron and below, and then there's another size range that's quite a bit larger. So typically, at least you find a bimodal size range. And the bimodal size range could be coming from two factors, right? It could be the particles forming out here are initially nanometer in size. And if you remember when I showed you that particle quenching on the surface of a silicon wafer, if you did an SEM on that, you would find those particles are probably in the order of 10 to 50 nanometers in diameter. They could start growing up to the smaller size, and the original particle could be then responsible for the larger size. Does the aluminum oxide, accumulate right on the original particle, and therefore it would scale initially with the original particle size. So you can see at the last comment here, from a practical viewpoint, a mean size distribution of 10 to 25 micron is ideal for stabilizing combustor instabilities in the 200 to 400 hertz range. So that's sort of the medium frequency range, not the real high buzz frequency where you'd want maybe 2 micron and less. So some factors influencing agglomerates. Large agglomerates result in large residual oxide droplets. High aluminum content in the propellant leads to large agglomerates. Factors that increase the burning rate, reduce the amount and size of the agglomerates. Ingredient particle size distributions that yield large concentration of aluminum in the propellant particle packing pattern give large agglomerates. Use of burning rate suppressants in binders that produce increased melts and carbonaceous residue on the burning surface usually lead to increased agglomeration and agglomerate size. Modification of the aluminum particles in a way to minimize interparticle sintering reduces agglomeration, for example, coatings for aiding ignition or pre-oxidation. And cross-flow environments tend to decrease agglomeration as well because I'm obviously dragging the particles off the surface. Okay, so those trends, were generally for micron particles burning in composite propellants. Here's a couple pictures of looking at just a strand burning, and it's an AP composite HTBB strand of a composite propellant. And on the left-hand side, what's been added is 43 micron aluminum. Obviously that's the mean size. And on the right-hand side, what was added to the composite was 80 nanometer aluminum. And two things you can observe right away. The purple line indicates that when the picture was taken, where the surface is. So in this picture, the surface located here. In this picture, the surface is located here. Okay, so with the micron particles, you can see basically large agglomerates sort of forming, and they're coming off the surface and mostly burning some distance away from the surface, just as I showed you before. However, when I put in the nanometer particles, you can see they ignite, a majority of them ignite very close to the surface, and I have a lot of burning very close to the surface. And these temperatures are going to be very hot again, and I'm going to have closer heat feedback to the surface than for the micron particles. So I should expect an increase in the burning rate then, of the composite propellant. And indeed, here's an example where I'm plotting the log of the burning rate versus the log of the pressure. The lower curve here is for a composite propellant of AP HTBB with just micron particles, and the upper curve is where 50% of those micron aluminum particles were replaced with nanometer particles. Okay, and you can see the increase in burning rate. So that's a favorable result still. But if we go a little further, this is what we see. So on the left is the burning of a micron aluminum particle in that composite. And this looks very similar to the movie that I just showed you. Coming off of the surface, there's an aluminum particle, and you see sort of this flame zone around a large aluminum particle. But what's happening with the nanometer aluminum, because of the small particles, and now I have a lot of particles that are close to each other in the condensed phase because I have the same loading of aluminum particles, they're touching each other. And by the time they get to the surface, remember you also lower the sintering temperature if you have a nanoparticle. So they're actually sintering together, and I'm losing surface area of the particles before they leave the surface, and they start behaving more like a micron particle. So what that's telling me is I'm not getting the full efficiency out of the nanoparticles, because at some point they're starting to look more like micron particles. So the sintering and reaction times are similar. So if you, for a nanoparticle, if I do some back-of-the-hand calculations and calculate what a sintering time is, you'll find it's at the same order as the reaction time, and as a consequence of that, there's a rapid loss of the nanostructure. So I'm going back to, again, that plot of the burning time versus diameter for aluminum particles, right? And this was the large particles, which I showed you before was d to the 1.8, close to d squared for large particles. Then I showed you as we went to small particles, this is what the burning rates look like to generate those burning times for different temperatures. But that's not what would have been expected because, as I told you, this is about d to the 0.3, and what simple theory should have told me is this should have went as d to the 1. So the anticipated times I should have expected should have fell within here as I decreased the diameter. So the particles aren't burning as fast as I thought they should. And so the question is why? Well, one reason is, just as I showed you, you could have a misrepresentation of the actual particle size due to the active sintering and particle aggregation during the experiment. So these experiments were conducted not in a composite propellant, but they were just conducted in air or oxygen. So they were sort of isolated particles, but there still could have been, a nanoparticle, if I look at it, a lot of time is a string of nanoparticles. It's like a soot particle. And the primary, you have a primary particle, and then you have a small aggregate that maybe have, 10 of those particles joined together. And those particles can join, they have a fractal dimension to them. And so before they burn, they could have actually sintered together, and we don't know the original size. So in this case, maybe, I thought this was maybe a small particle here, but because of sintering, maybe it really had a diameter over here. So that may be one reason. People have shown the fractal dimensions of the particle aggregates can actually affect the burning process. And as I said, we talked about before, the small particle size relative to the molecular spacing, the large Newton number, that could also affect the heat transfer process and affect the burning time. So I note difficulties in interpreting experimental data places more importance on predictive modeling. Two major constraints have limited further investigation, characterization, and implementation of nanomaterials. Their nanometer scale dimensions and the inherently high surface areas reduce their usability. A similar solids loading cannot be achieved. So if I just put nanoparticles and substitute them at the same mass loading into a prepolymer, right away it'll consume all the liquid and it'll all be coated on the surface. And I won't be able to work with it because the viscosity is too high. And particle-particle interactions dominate, making the dispersion of such particles nearly impossible. So there's been, this is some results of John Buckmaster and Tom Jackson, who was looking at, again, why this value of n to the 0.3. The surface roughness in the presence of cracks in the oxide layer may alter the relationship between the particle size and the surface area for chemical reactions. And what they show is that relationship is affected by essentially the fractal dimension of the particle system. Okay, and typically for these small nanoparticles that are joined together, the fractal dimensions are between 2 and 3, and they argue then that the burn time is going to scale as the particle diameter to the 3 minus the fractal dimensions, and if n varies from 1 to 0 as the fractal dimension varies from 2 to 3, and as a consequence of that, you're not getting the value of d to the 1 when you get smaller dimensions. This is some work that was done by Mike Zachariah that was arguing that basically sintering was occurring of the particles, and he basically calculated showing that the sintering time is of the same order as reaction time. So you can see here's the initial sort of array of nanoparticles, and as they heat up, they start to agglomerate, and you end up getting a much larger particle than you thought. So the question arises then, how hierarchical organization of nanostructures may be exploited in reactive energetic materials. So if I start off with a nanoparticle, how can I manipulate it to put it in an energetic material? Obviously, I could coat it with a ligand. If I coat it with a hydrocarbon ligand, then it's going to look like basically the surrounding polymer. So it's not going to, it'll change the viscosity of the mix. You can also change the energetics of the system. And then you could actually assemble these nanocomposite particles to maybe the mesoscale. And so if I'm working with mesoscale particles, that's also going to change the viscosity during the mixing process. So now you can think of designing this mesoparticle to have nanoparticles embedded in it with interstitial material that's beneficial to the reaction process of the nanoparticles. For example, right away, the interstitial materials could prevent the nanoparticles from sintering as the mesoparticles being heated up. And if I think about it, I could also adjust the interstitial material so that it's going to gasify at a particular temperature. Suppose I find a material that decomposes near the surface temperature of a burning composite AP HDPB propellant. Then when that mesoparticle gets near the surface, just as it's coming off, as it heats up, the interstitial material will gasify and basically explode the mesoparticle, shattering all over the place little nanoparticles, which didn't have a time to sinter. So you can now start thinking how a design process can go in and building these materials from the ground up. And then how do I assemble these mesomaterials to the macro scale? Right? Do I just go through the same sort of mixing process that I mentioned before, where you take the prepolymer, you put in the mesoparticles, you mix it like you were baking a cake, and you put in the curing agent during the casting process? Or do you start looking at, different lithographies, 3D printing techniques to actually put the particles where you want them? Okay, so I want to spend a little bit of time talking about, man, time went quick. So I guess we're due for another break, right? Is that right? In 7 minutes? Okay. So I want to talk a little bit about, what's been done in terms of this concept of nanoengineering these particles, looking at how we can start from the ground up to the larger scale. Okay, a couple other things you got to realize about nanoparticles. Because they're very small and the oxide layers are thin, so I have small length scales, they can age much more than micron particles. Any little reaction at the interface, if the particle sits out on a shelf and it absorbs moisture, it has a lot of surface area, it can actually age the particle. So again, one of the ideas that is to prevent the aging is, again, passivate the particle. Put a layer of something over it that's going to prevent oxygen from getting to the surface. Okay, and you can see here, this was originally nanoparticles and how quickly the relative energy content changed with time in terms of days. Okay, so again, the idea is how can I passivate the surface and what's been done? So I'm not going to go through all these, but give you an idea. Nanoparticles have been encapsulated with polymers and other metals. So in terms of polymers, carboxylic acid, halides, alkyl substituted epoxides, and azides have all been coated on nanometallic particles. Aluminum, boron, magnesium, titanium, zirconium, and silicon have all been encapsulated. Longer change and greater hydrophobicity have had greater stability. Currently, the passivation is done with ligands off the shelf, so people have not taken time to specifically design a particular ligand for a particular use yet. Fundamental studies on the bonding strengths and uncapping temperatures and reaction mechanisms are very limited. So again, looking at molecular dynamics calculations and quantum mechanical calculations, there's been very little fundamental studies and looking at bonding energies and how ligands might break off and how you could tune that to your advantage. Metals themselves have been coated with other metals. So for example, nanoaluminum has been coated with nickel, palladium, and boron. At the nanoscale, thin coatings often lead to balling and insufficient coverage. So if I put, for example, on a nanoaluminum particle, I put a very, very thin layer of nickel, what you'll often find is because of surface tension during the fabrication process, the nickel balls itself into even smaller particles on the surface. And so it's very hard to get a very thin layer of nickel. I'd actually have to increase the thickness quite a bit to get complete coverage. Okay, so one of the questions you might ask, and this is another area of research, how small can I make a nanoparticle? So there's been a lot of interest lately in what's referred to as clusters of metallic particles. And these are clusters that start off with very few atoms in their structure, 8, 10, 13, 15, 70 on up. Okay, and they would become very reactive. You could passivate those surfaces. And there's some unique characteristics about it. What I note here, reactions of metal clusters with small molecules often depend on the cluster size and vary discontinuously with the number of atoms in composition rather than the scale linearly with size. So example, one atom addition to the cluster can make a big difference. I think if you take, for example, aluminum 12, and you go to aluminum 13. One reacts significantly with water and oxygen, and if I go and add one more aluminum atom, it doesn't. So there's a lot of science, and there's been a lot of research in this area, and some people have said you can actually, depending on the size, sort of have an analogy to the characteristics of the periodic table in terms of reactivity. So sort of adding a third dimension to a periodic table. So what I show here is a couple examples of what's been made. The first in terms of metalloid clusters, one of the biggest initial clusters was basically aluminum 77. So there's 77 aluminum atoms. So you can see that cluster is made up of a cluster of smaller size that's encapsulated with a larger size. And then eventually it's passivated with a relatively large ligand surrounding it. Okay, and people have made the precursors of these clusters, and I give a couple examples here. They've added them to solutions, and if you add them to a solution, say of a liquid fuel, you actually find a different characteristic in burning rate than if I just made a simple slurry of adding a metal particle. You actually get liquid phase reactions between the cluster and the fuel that leads to disruption and different burning characteristics. So this is an area, I'm not going into it, but it's an area that people are looking to in the future. It's a high-risk area where cluster research could go into in terms of practical usage. This is an example of the surface passivation that was done by fluoroalkyl carboxylic acids. And in this particular case, the question was what type of bonding was occurring at the surface. And you can see on the right here, you could have a single oxygen atom bond to an oxygen atom of the aluminum oxide, or basically a bridging. And I think what the researchers found out was that the bridging connection was the most common. This is a case where, again, an iron particle was coated with oleic acid, and it was made through a sonochemical method. And the idea here was they wanted to add these particles to jet fuel. And they recognized that jet fuel has a certain amount of oxygen in it. And if the newer turbine engines are going to be running under conditions where the fuel, before it gets injected, is going to go supercritical, it gets pretty hot. And what they've found is that if there's any oxygen absorbed in the fuel, it starts to oxidize and start leading to coking reactions. And so right at the injector, they have problems. So the idea behind this was to basically take nano iron particles, coat them, and just before that temperature occurred, basically the ligand would come off, and the iron would preferentially then react with the oxygen to create iron oxide, prevent the coking reactions that would lead to carbon deposits on the surface of the fuel lines. And here's another example of making particles where basically in a sol gel method using sonochemically mediated liquid slurry, where basically a titanium chloride was mixed with lithium aluminum hydride with lithium boron hydride, and what they ended up then was with a complex particle of titanium aluminum boron hydride. And in these particles, because of their structure, basically didn't have an oxide layer. And out of that solution came basically a salt, which they could easily remove then, and they could work with those particles. And the particles basically showed that they're stable in a high energy state, they're amorphous, have a low sensitivity to air after processing, retain some hydrogen, about 10% with low temperature heat treatment, and have a mass density of about 2.6. I guess what the point is, I'm trying to show you that there's a lot of research in this area, and different types of particles are being made using different types of techniques. We actually took those particles and did some closed bomb studies with them to look at the completeness of the reaction. And what's shown here on the left is you're looking at the heats of combustion of these combined metal particles against aluminum, boron, and titanium. And what you see is the measured theoretical heat of combustion was the highest for these composite particles. And if you were to add these particles, say, to a hybrid rocket motor, you can actually get an increase in basically the specific impulse. Okay, so let's take a break now, and I'll show you how basically the thought process is in terms of incorporating it into larger scales.